All right, so a little more here on the fundamental theorem of calculus. So remember the other day, wrong screen, there we go. We took a look at the fact that the rate of change of the area function, which is what this is right here, or written in integral form, is the boundary curve, which is remarkable. It gives us a link between derivatives and antiderivatives for evaluating what we call definite integrals. And then we have the second part of the fundamental theorem, which is the evaluation part of the theorem, that says given an area function, which could be any antiderivative, we just need to evaluate that function at the endpoints, which beats the heck out of doing Riemann sums. Pretty complicated. And for a lot of functions, it's like almost impossible to do. So let's look at a couple of examples using both the fundamental theorem part 1 and the fundamental theorem part 2. So the first thing I'm going to take a look at is the idea that if we take the derivative of a definite integral, and let's say we had something like 2x for the function t squared dt. That link between the area function, which is the definite integral, and the derivative pretty much means they cancel each other out. And so this is going to be equal to x squared, which is kind of cool. A little catch goes in there for certain situations. So if we try that again, take the derivative of a definite integral, and suppose we had the integral from 0 to x squared of the cosine of t dt. Since there is an evaluation going on here at the endpoints, kind of hidden, we have a function within a function here. And so we have our cosine function right here, but we also have this inner function there. And so whenever I take a derivative of a function within a function, the chain rule applies. So in this case, this is going to be equal to, well, the fundamental theorem, ignoring the endpoints for a minute, say it's going to be related to the cosine. And the endpoint is x squared. The catch with the chain rule says we have to multiply by the derivative of the inner function. And so we're going to have a times 2x to go with this one. So we have to be careful. If we're just evaluating an integral as an area function, that means the endpoint is an x, and the beginning point could be any real number. That one doesn't matter. 1, 0, it's irrelevant. We're okay. Once we throw in something other than just x as the endpoint, then the chain rule pops in, and we have to evaluate it using the chain rule. All right, let's play around with some other functions. So then it becomes, using the fundamental theorem, becomes a matter of, do we know an antiderivative based on derivatives that we did before? So let's take a look at the definite integral from 1 to 9 of x minus 1 over the square root of x. Now, that is not a common function that we've seen as the derivative of something before. And so we're going to have to rewrite this algebraically. And often that's going to be the case here. So what I'm going to do is I'm just going to carry along my definite integral symbol, and I'm going to rewrite this as x is being divided by the square root of x. And we have that minus sign, and the 1 is also divided by the square root of x. And all of this is part of the integral, so we should put in parentheses, dx at the end. Then what I can do is view the square root of x as a power of x, x to the 1/2. And so I can rewrite this yet again. And so I would have x to the first divided by x to the 1/2. So my exponent would be 1 minus 1/2. And so that would just be x to the 1/2 for the first one, minus 1 over x to the 1/2 would be x to the negative 1/2. And as we talked about before, to finish this, I need another trick. And so the other trick is we know that if we take the derivative with respect to x of x to the n, we're going to get n times x to the n minus 1. Now, when we reverse that and do an antiderivative, the power is going to, in the other direction, the power from here to here is going to increase, right? N is 1 bigger than n minus 1. And instead of the multiple being on this side, I'm going to have to divide it to the other side. Okay. So let's see, can I grab that sucker? Let's try. So this n is going to have to go in a division over there. And so let's throw in that. All right, so the derivative of x to the n over n would just be x to the n minus 1. And so again, note, going the red arrow way would be an antiderivative. And so the power goes up by 1 and we divide by that new power. So what that means for these guys over here, the implication, it's right underneath, would be that the antiderivative for x to the 1/2 would be to increase that by 1. So that would give me x to the 3/2. And then I'll have to divide by 3/2. Minus increasing 1/2 by 1 would give me x to the positive 1/2, and I'll have to divide by 1/2. And then I still have to evaluate the boundaries. So what I usually write next is I put a little bracket around it with a reminder to myself that I still have to evaluate the endpoints. So this function right here is my antiderivative for the original function over here. And so now the evaluation theorem says plug in your endpoint starting with the right endpoint. So we could clean that up algebraically a little bit, but I'm not going to worry about that yet. So I want to then take the first part, 9 to the 3/2 over 3/2 minus 9 to the 1/2 over 1/2. And then I'm going to subtract the left-hand endpoint. So that means I'm going to have a 1 to the 3/2 over 3/2 minus 1 to the 1/2 over 1/2. And now we have arithmetic to do. So either whip out your calculator or help me out here. Let's see, the half part there means take the square root of 9. Square root of 9 is 3, and then cube it, that gives me 27. So that's going to give me here, what, 27, and dividing by 3/2, the same as multiplying by 2/3. So that's kind of nice. That 3 will divide into the 27. And the next part, let's be safe, put that parenthesis back in. Again, I'll have 9 to the 1/2, which is 3, divided by 1/2 is times 2. 3 times 2 is 6, so that should be 6. Minus, and then over here, that's 1 over 3/2, which is 2/3, minus 1 over 1/2, which is 2. And let's see, do I have any more room underneath here to write? So we'll just take it over this direction. So cleaning that up, let's see, what do we get? We get a 9 times 2 is 18. 18 minus 6 is 12. Minus 2/3 minus 2. That would be 1 1/3. And if we take 1 1/3 away from 12, let's see, that should be 10 and 2/3. And so that should be the answer there. So let's hope we're right. All right, let's do one more. And this one is a wee bit tricky. And it's in the homework. And based on the textbook, it's below this up a touch, I think this really should have been in section 5 because they don't go over anything similar to this in the book. Let's see if you up. All right, so we're going to play with this sucker right here. Page. Square root. All right, so you can remember all that. Try. So we have the integral from 0 to 6 square roots of 3, and the fraction 13 over 144 minus, did they use an S in there? Yes, they used an S. Over S squared, and that whole denominator is in a square root. Oof, that looks nasty. I like to put the DS over here instead of in the numerator. I always thought that was weird. All right, so we got to think antiderivative for this. So whenever I have 1 over stuff with squares plus or minus, I think inverse trig functions. So I looked up a table of derivatives. Blow this up. So inverse trig functions, this looks like the inverse sine, or that's often called the arc sine. But we have a little catch. Instead of a 1 in the denominator here, we have a 144, which complicates matters a little bit. So I'm going to have to do a little bit of algebraic manipulation on that to get it to match this right here. So what I know right now is this has something to do with the inverse sine as an antiderivative. So now we get to play around. All right, so let's see. I can, let's see, we can pull out that 13, right? So we have 13 times the integral from 0 to 6 square roots of 3, and that gives me 1 over the square root of 144 minus s squared ds. All right, so let's see. That 144 is kind of a pain. I would like to divide that out. So if I were to do so, it's going to get a little messy, but let's go for it. I would like to divide by 144 there, divide by 144 here. Now that 144 is inside that square root. So basically I just multiplied the denominator by the square root of 1 over 144. So to compensate, then I'd better multiply the top by the square root of 1 over 144. All right, note 144 is 12 squared, so basically I multiply top and bottom by 1/12. And the reason I'm doing that is it's my belief that this will then look more like that derivative formula. So switch back to blue. So what I think I have right now is 13 times the integral from 0 to 6 square roots of 3. And now I have a 1/12 in the top. And in the bottom, I have the square root of 1 minus, and that's really s squared over 12 squared, which I could write as s over 12 squared, that's a square, ds. All right, so now a little bit of thought on a derivative. I had the sine inverse, often called the arc sine, of, let's call it s over 12. And then I was asked to take the derivative with respect to s, of that. Then the rule I looked at earlier says, well, that's going to be 1 over the square root of 1 minus s over 12 squared. The chain rule says you have to multiply by the derivative of s over 12, which is 1/12. Okay, so now notice here, highlighter, gray box, all right, that if I have all of this stuff, the antiderivative is simply the sine inverse of s over 12. Check it out. What do I have over here? I have my 1/12 as a multiple, and I have a square root of 1 minus the quantity s over 12 squared. So the stuff I've highlighted in yellow is the derivative of the sine inverse of s over 12. So I'll do that in another way in the next video, just for fun. And let's switch colors back to blue. So what I have now is that 13 is still chilling out, waiting to be dealt with. And once I come up with an antiderivative, I put it in brackets. So I believe the antiderivative for the stuff I highlighted in yellow above is the sine inverse of s over 12, because if I were to differentiate that, I would get the stuff in yellow above. And I still have to consider the evaluation of that from 0 to 6 square roots of 3. So a lot of times when we're playing around with antiderivatives, if we think we know an antiderivative, it's always a good idea, as I did in left and green there, to take the derivative of it to make sure you do get back what you thought you started with. And we'll get used to that idea because we're going to do it pretty much every day from now on. All right, so now comes the fun evaluation part. So let's see, the 13's chilling out. And then I'm going to have what, the sine inverse of 6 square roots of 3 over 12 minus the sine inverse of 0, because the fundamental theorem part 2, the evaluation part, says once you have an antiderivative, plug in the right-hand endpoint and then subtract the evaluation of the left-hand endpoint. All right, so cleaning that up, really the sine inverse of the square root of 3 over 2, isn't it? 6 goes into 12 twice. And so thinking about a unit circle for a second, n is a y value, square root of 3 over 2 is 0.8 something, that's way up here. So what angle goes with the y value up there? And that looks to me to be what, the square root of 3? Sorry, not square root of 3, pi over 3. Yeah, pretty sure that's right. And then we know that the sine of 0 is 0. All right, so let's move that sucker out of the way. Like this. Come over to this direction. So I have the 13 on the outside times pi over 3 minus 0. So I think the answer is 13 pi over 3. Okay, so could we check this? Yeah, actually we could check this by using something like GeoGebra and asking about the area. But since I have the homework up here, I could just say, hey, did I get it right? So I think it is 13 times pi divided by 3. Let's see, zoom out so I can find the check answer button. Woohoo! That was exciting. All right, so I'm going to take a break there on the evaluations, and I'm going to come back with another recording based on some cool applications of the fundamental theorem. Ta-ta.